Welcome back to the deep dive. Today, we're doing something a little different.
Mm-hmm.
Usually, we spend our time talking about the magic tricks, the poetry the AI can write, the images it can generate.
Right, the wow factor.
Exactly. That's stuff that gets everyone excited on social media. But today,
We're shifting gears completely. We're putting on the hard hat.
we are entering the construction zone. And, not just any construction zone. We're talking about the absolute bedrock of the financial world.
That's it. I want you, the listener, to just close your eyes for a second. Forget about being a hobbyist coder, hacking away on a weekend project in your garage.
Okay.
I want you to imagine you are the chief architect for a massive, multinational financial institution. Let's call it, I don't know, Global Fortress Bank.
The stakes just went through the roof.
I mean, the highest stakes imaginable. You have billions of dollars in assets flowing through your digital pipes every single day.
You've got regulators in 3 different continents. You've got the SEC, the BaFin in Germany, the FCA in the UK. They're literally breathing down your neck.
Constantly.
And your CEO just walked into your office, looked you dead in the eye and said, "We need to integrate generative AI into our core banking loops, and we need it yesterday."
And that is the moment where the cold sweat starts.
Right.
Because in that environment, just getting it to work is actually the easy part. A junior dev can get a model to say, "Hello, world," or, write a haiku in an afternoon.
Right. But can you get it to say hello world without accidentally leaking a VIP client's portfolio data to a server in a jurisdiction you're not even legally allowed to operate in?
That's the real question.
Can you get it to execute a trade without a single millisecond of latency that might cost the bank millions? Can you update the brain of the bank, the model itself, without crashing the entire transaction system, the one people rely on to buy their groceries?
Exactly. That is the mission for this deep dive. We are stripping away the hype and looking at the enterprise architecture for AI. We're moving beyond the Hello World tutorials and deep into the world of hard constraints. We're talking about the fortress and the brain.
And we're doing this by dissecting a specific set of architectural pillars. We've pulled together the latest infrastructure documentation. We aren't just speculating here. We are looking at the blueprints.
The actual plan.
We're going to look at 3 main things. First, compute, the raw horsepower. We'll get into the actual silicon you need to run these beasts and, maybe more importantly, how you control it.
Which is often, more important than the speed itself.
Second, sovereignty. How do you build an AI when you are legally forbidden from talking to the public internet?
It sounds like a paradox.
It does, but for our banking listeners, that's just Tuesday.
It's the daily reality. The no internet constraint, as we'll call it.
And third, operational safety. How do you perform brain surgery on a patient who is, at the same time, running a marathon?
I love that analogy. It's terrifying, but it's incredibly accurate.
So let's unpack this. Our approach today is all about constraints. I think that's the key takeaway for everyone listening. In a startup, you do whatever's fastest.
It's a market.
In a bank, you do whatever prevents you from going to jail or losing $1 billion. So the mantra for today is, you can't do X because of regulation Y, so you must use Z.
Precisely. The constraint dictates the architecture. It's not about picking tools because they're cool or they're the new hotness.
Yeah.
You pick them because they are the only ones that fit into the legal and technical box you're trapped in.
Okay, let's start with the engine room then. Section 1, the compute layer. This is where the rubber meets the road, or guess where the silicon meets the electricity.
It's the foundation of everything. I mean, if you get this wrong, nothing else matters. You'll either be too slow to compete or, frankly, too broke to even finish the project.
Let's set the scene. You're at our Global Fortress Bank. Your task is to train a massive model. Let's say you're building a specialized large language model just for understanding complex derivatives contracts.
Okay, so a very specific, high-value task.
Exactly. This isn't a generic chatbot. This is a specialist. It's a multi-terabyte beast of a model.
So we are talking billions, maybe trillions of parameters.
Yeah.
This is not something you run on a laptop. You can't just download this to your MacBook Pro.
Not even close. So you have to make a hardware choice. You look at the infrastructure menu and you see 2 main options. Option A cluster of standard GPUs. Everyone knows them. Everyone uses them for gaming, for crypto.
The workhorse.
Option B, a TPU pod.
The tensor processing unit. Google's custom silicon designed specifically for this kind of math.
Now, intuitively, as an architect, my first instinct might be to just look at the spec sheet and ask, which chip is faster.
Sure.
If chip A does 100 teraflops and chip B does 120, I pick chip B simple.
This seems logical.
But looking at our source material, the decision for a bank operating at the scale, it actually hinges on something else entirely. It's not just the chip, it's the wiring.
It is the wiring. This is such a crucial distinction. It's what separates, a junior engineer from a senior architect.
Yeah.
When you are training at that scale, these multi-terabyte models, you are not doing it on one chip.
It's impossible.
You physically can't. The model is way too big to fit in the memory of a single processor.
So you have to break it up. You have to shard it somehow.
You have to.
Yeah.
You have to distribute the math across thousands of cores. You slice the model into pieces, that's called model parallelism, or you slice the data into pieces, which is data parallelism.
Yeah.
But as soon as you do that,
Yeah.
the bottleneck usually isn't how fast the math happens on the chip anymore. It's how fast the chips can talk to each other to share the results of that math.
Because they have to stay in sync if one gets ahead of the other.
Exactly. Every single millisecond that one chip spends just waiting for data from another chip is a millisecond of wasted compute.
Yeah.
And that adds up incredibly fast.
This is where we get into the acronym of the hour from our sources, ICI.
ICI. Interchip interconnect.
What exactly is that? It sounds like something I'd need a specialized screwdriver to install.
You're not far off. Think about a standard GPU cluster. Often, those chips are connected using commodity networking.
Like just standard Ethernet cables.
Pretty much. Super fast Ethernet, sure, but it's what runs the internet. It's a general purpose. And that means it has overhead. It has to wrap the data in packets, address them, route them, check for errors, acknowledge the receipt.
It's like sending a letter through the regular mail system, but just inside one office building.
That's a great way to put it.
You have to put it in an envelope, write the address, put a stamp on it, take it to the mailroom.
Even if the mailman is sprinting down the hallway, the process itself has friction. The latency, that delay, it just adds up.
So whereas ICI is different how?
ICI is a specialized, high-speed network designed specifically for direct chip-to-chip communication. It's native to the TPU pods. It provides incredibly high bandwidth, and this is the crucial part, extremely low latency. It completely cuts out the middleman. There is no mail sorting room. It's a direct, dedicated line.
So to use an analogy, a standard GPU cluster with Ethernet is like a team of brilliant geniuses in a huge, noisy stadium, all shouting answers to each other across the field.
That's a perfect visual, yes.
They're smart, they can do the math in their heads instantly, but the communication is slow. One genius yells, "Hey, what did you get for X?" And the other one yells back, "I got 5." But with all the crowd noise, the first guy goes, "What did you say?"
I said 5.
4. And they have to wait to hear the answer clearly before they can even start the next calculation. That waiting time, that latency accumulates over billions and billions of operations. That is what kills your training time. It's not that the thinkers are slow, it's that the room is too loud.
But a TPU pod with ICI is like, what? Is it like a Vulcan mind meld? That's basically it, yes. It's like telepathy. The brains are linked directly, often with a dedicated optical fabric. This allows for incredibly efficient model parallelism and data parallelism. You can split that massive derivatives model across thousands of cores, and they act as a single coherent unit.
So they are effectively one giant brain.
One giant distributed brain.
So the architectural decision here for our listener, the architect at Global Fortress Bank, is clear. If you are training a foundation model from scratch at massive scale, you go with a TPU pod specifically because of the ICI. That constraint leads to solution thinking.
Exactly. If the speed of training your model is your primary constraint, the interconnect is almost always your bottleneck.
Yeah.
ICI solves that bottleneck.
Right.
So you're not just paying for the chip, you're paying for the network that binds all the chips together into a supercomputer.
Okay, that makes perfect sense. So we've got the hardware sorted. We're using TPUs for the heavy lifting. Now let's move up a layer in the stack. Let's talk about the abstraction layer. This is all about the human element. How much control do you give your developers versus how much do you manage for them?
It's a classic buy versus build or, manage versus rent debate. But in the cloud era, it's really IaaS versus PaaS versus SaaS. Infrastructure, platform, or software as a service.
And we have a perfect case study in the notes here, a fictitious company called Summit Dynamics.
Summit Dynamics.
Right.
This is a great example because it shows that a single company, or our global fortress bank, isn't just one type of user.
Right.
They have different tribes within the company, and they all have radically different needs. An architect has to please all of them, which is that's usually impossible, but that's the job.
That is the job. So let's break down these tribes. Tribe 1, the Innovation Lab. These are the deep tech researchers. They're in the basement, hoodies up, drinking energy drinks. They aren't building the banking app today.
No, they're inventing the future of finance for 10 years from now.
Exactly. They aren't just using models, they are inventing new neural network architectures. They care about the math, the fundamentals, and they care about the very, very bottom of the software stack.
Oh, absolutely. Their constraint is, don't touch our stuff. They need to install custom kernels. They want to mess with the guest OS. They want to be able to manually tweak the NVIDIA drivers to squeeze out every last drop of performance for some experimental architecture they dreamed up.
So if you give them a managed platform where they can't get root access or see the file system,
They will quit. They'll walk. They need to be able to break things.
Yeah.
They need to be able to crash the OS just to understand why it crashed. That's how they learn.
so what do we give them? We can't give them a lockdown, pretty interface.
No. You give them ISS, infrastructure as a service. In the Google Cloud world, that means compute engine.
Raw VMs.
You give them raw virtual machines. You tell them, look, we will handle the physical hardware maintenance. We'll make sure the power is on and the hard drives don't literally melt. But inside that virtual box, that's your problem. Here's your root access.
So you're giving them the keys to the car, but you're also handing them a wrench and a full toolkit and saying, if it breaks down on the highway, you're the one fixing it.
Precisely. And they love that. That's their playground. They want that control.
Okay. So, constraint. Must control the kernel and the OS. Solution. Compute engine. That's tribe 1 sorted. No, tribe 2. Product engineering.
The builders.
These are the folks building the actual mobile banking app that millions of people use every day to check their balance. They want to write Python code. They want to ship features. But they do not want to be woken up to patch Linux servers at 3 a.m.
Absolutely not. They want velocity. They don't care about the GPU driver version. They care about the API response time. Their whole world is about deploying code, not managing infrastructure.
Yeah.
If they have to spend 3 days configuring a firewall,
That's a waste.
that's 3 days they aren't building banking features that make the company money.
So what's the solution for them? You can't give them a raw VM.
No, that would slow them down. You move up the stack to PaaS platform as a service. Specifically, a tool like Vertex AI. This provides a managed infrastructure. You bring your code, your Python script, your model training job, and the platform runs it. You don't manage the servers, you manage the logic.
It's all about eliminating what they call undifferentiated heavy lifting.
Exactly. If the
Yeah.
server needs a security patch, Google does it. If the storage drive is getting full, Google expands it. The product engineers just keep coding and shipping features.
Yeah.
It's about abstracting away all the boring stuff so they can focus on the business logic.
Okay, that makes sense. And then tribe 3, the communications department.
The folks writing the press releases and the internal all-hands memos?
Right. They don't know what Python is. They think a kernel is, a piece of popcorn.
Right.
They just want an assistant, something to help them draft emails or summarize a long meeting transcript.
For them, you go all the way to the top of the stack. SaaS software as a service.
Like Gemini for Workspace.
Exactly. No coding, no servers, just a utility. It's like electricity. You flip the switch and the light comes on. You type a prompt, you get text back. End of story.
I love this breakdown because it really shows that a good enterprise architect doesn't just pick the one AI tool for the company.
No.
They map the specific level of control required by the user to the correct service layer.
It has to be a portfolio approach. If you try to force the innovation lab to use Gemini for Workspace, they can't do their job because it's way too limited.
And if you force the comms team to use Compute Engine and learn Linux commands,
They can't do their job because it's infinitely too complex. You have to match the tool to the user persona. It sounds so simple, but you'd be surprised how many large organizations try to force everyone into one box because it seems easier to manage from a central IT perspective.
and it ends up being one size fits none.
Exactly. And in a bank, that kind of friction just slows everything down to a crawl.
Okay, so let's move on to section 2. We've built the engine, we've chosen our chips and our service layers. Now we need to build the walls. This is the fortress.
This is where it gets really, really interesting for our banking listeners. This is where the lawyers get involved in the architecture meeting.
We are talking about sovereignty and isolation. Let's start with the big one, the no internet constraint.
The air gap, the digital fortress.
The notes mention a very specific scenario, a German insurer or a bank. In Germany, and frankly in much of the EU, privacy laws are
Let's just say they're robust.
Very robust. They view data privacy as a fundamental human right, not just, a consumer preference.
Yeah.
And the regulators there, the BaFin, the GDPR authorities, they do not mess around.
So the constraint is simple, but it's brutal. The generative AI platform must run only in their own data centers on their own hardware.
This is a complete showstopper for a lot of modern AI strategies. It just breaks them. It does, right? Because think about how most people use AI today. You go to ChatGPT or you use the Gemini API. You make an API call to the cloud. You send your prompt to some massive supercomputer in Oregon or Belgium. It processes it, and it sends the answer back.
But if you're this German bank, you cannot send that data out. You cannot use the standard cloud-hosted Gemini API. It's physically and legally impossible. If customer financial data leaves your premises, if it even touches a public cloud network for a millisecond, you might be breaking the law. You could lose your banking license.
So, do they just give up? Do they go back to using abacuses and spreadsheets?
No. They have to change the architecture. The thinking has to shift. You can't go to the model must come to you.
And this brings us to the world of open weight models.
Correct. If you are cut off from the big sauce APIs like the closed source Gemini API, you are restricted to using models where you can actually download the weights, the mathematical definition of the model's brain, and run them yourself.
So we're talking about models like Llama or Gemma or others that are available in places like the Vertex AI model garden.
Exactly. So the architect's job here shifts dramatically. Instead of managing an API key and a billing account, they are now managing the raw infrastructure to host these massive open source models on-premise, or maybe in a private cloud environment.
That's a huge shift in responsibility.
It's a massive trade-off, and the architect needs to be completely transparent about it. You lose the incredible ease of serverless AI. You take on the full responsibility for uptime, for latency, for hardware provisioning. You have to be the plumber now. You have to deal with out-of-memory errors at 2 a.m. You have to figure out how to shard the model across your own GPUs.
But the upside is?
The upside is you satisfy the non-negotiable regulatory requirement. You achieve total isolation. No data ever leaves your four walls. You have built a truly sovereign AI capability.
It kind of turns the normal cloud benefit on its head. Usually you go to the cloud to offload responsibility. Here, you're using a cloud provider's tools, specifically something like the Vertex AI model garden, just as a library or a catalog to fetch the model, but then you take it and run it yourself.
That's the key distinction. The model garden bridges that gap. It's a catalog. It says, okay, you need an open model because of your regulations. Here is Llama 3. Here are the pre-built container images. Go run it on your private rig. It simplifies the deployment of these sovereign models, even if you are ultimately running them in a digital bunker.
Speaking of sovereignty, let's touch on a related concept, data residency.
A slightly different flavor of the same core problem.
The scenario here is a government agency or maybe another EU bank. They might be okay with using the cloud, so they don't need to be totally on-premise, but the data literally cannot leave the physical borders of the country.
Right. It's not about no internet. It's about no passport. The data cannot travel internationally.
So if I'm a bank customer in France, my data has to stay in France. It can't be routed through a server in Germany for processing, even if it's the same cloud provider and it's all encrypted.
Precisely. This is where the concept of cloud regions becomes a critical piece of the architecture. It's no longer just about picking the region with the lowest ping time or the cheapest price.
It's a legal decision.
It's entirely a legal and compliance decision. You have to meticulously configure your services, your Vertex AI processing jobs, your storage buckets, to guarantee that the bits and bytes never cross the border.
It's just amazing how geography has re-entered the chat in the digital age. We spent 20 years trying to make the world flat with the internet, and now we're building these very strict digital borders.
It never really left. We pretended it did for a little while. But when you're dealing with sensitive government records or financial data, borders matter. A server in the U.S. is subject to U.S. law. A server in France is subject to French law. And believe me, banks care very, very much about which judge has jurisdiction over their data.
That's a very good point. Now, there is a middle ground here, isn't there? We've talked about the all-cloud approach and the all-private bunker. What about the hybrid developer?
The pragmatist.
The source material mentions a company that wants the best of both worlds. They want to use a pre-trained open source model. Maybe they like the transparency of it, or they want to be able to fine-tune it heavily on their own data.
Right.
But they really don't want to build a data center to run it.
This is a very, very common use case. It's the, I want to use Llama, but I want you to run it for me scenario.
And the tool for this is?
Again, it comes back to the Vertex AI model garden, but you use it in a different mode.
Yeah.
Instead of downloading the model for self-hosting, you use the one-click deploy feature.
And that does what?
It takes that open model and it spins it up on Google's managed infrastructure, inside the correct region, of course.
So you get the open source model you wanted, but with the PAWAS, the platform as a service experience.
Exactly. It removes all the manual containerization. You don't have to write the Docker file. You don't have to worry about NVIDIA drivers. You just click deploy, and you get secure, scalable endpoint.
Yeah.
It's really the sweet spot for many enterprises who want the flexibility of open weights, but the convenience of managed operations.
Okay, that covers the fortress. We've got the chips with TPUs. We've got the model, whether it's sauce or sovereign. Now we need to feed the brain. Let's talk about the nervous system, the data architecture.
Ah, the fuel. Without the right data, the model is just an empty shell. I mean, it can speak perfect English, but it doesn't know anything about your bank or your customers.
There is a term that has completely taken over the industry in the last couple of years. RG, Retrieval Augmented Generation.
It's the standard pattern for enterprise AI now. I'd go so far as to say if you aren't doing R's, you probably aren't building a serious enterprise AI application.
For the listener who has maybe been living under a rock or perhaps just working on legacy COBOL systems, unpack RG for a second. Why do we need it? What is it?
Well, you don't want your AI to just hallucinate answers or rely on its training data from 2 years ago. That's useless for a bank. If you ask a standard model, what is my current account balance? It doesn't know. It can't possibly know. RAG is basically giving the AI an open book test. You store your company's knowledge, your internal policy manuals, your customer records, your product descriptions in a specialized database. When a user asks a question, the system first searches that database, finds the most relevant pages or documents, and then hands them to the AI, saying, use this specific up-to-date information to answer the user's question.
Simple enough in concept, but the architectural challenge is, how do you search for meaning? If I search for, how do I reset my password? A traditional database is just looking for the keyword password. But what if I ask, I'm locked out of my account?
A traditional keyword search might completely miss that. The phrases locked out and password reset are conceptually the same, but linguistically they're very different. There are no shared words.
So this is where we need vector search.
Right. We have to convert our text into numbers, into vectors. These are long strings of numbers, sometimes hundreds or even thousands of numbers long, that represent the meaning of the text in a multidimensional mathematical space.
And similar concepts have similar numbers.
Exactly. The vectors for locked out and password reset would be mathematically close to each other in that vector space, even though they share no letters.
So the big question for our architect listener is, where do we store these millions of vectors? Do we just, I don't know, dump them in a text file?
Please don't do that. You'll have a very bad time. You need a database that is optimized for this kind of search. The source material points us to a solution like AlloyDB for PostgreSQL, using an extension called pgvector.
Okay, why AlloyDB? Why not just a standard PostgreSQL database? Or why not one of these new specialized vector databases like Pinecone or Weaviate that you hear about?
It comes down to a few things: performance, scale, and crucially, integration. Vector search is mathematically intensive. You're comparing one set of numbers against millions of others to find the nearest neighbor. AlloyDB is a version of PostgreSQL that's been highly tuned for performance. It can handle the heavy lifting of that vector math much more efficiently than a standard unoptimized database. It keeps the latency low.
But here's the catch. The source gives us a really tricky scenario that explains why you'd choose a familiar relational database like AlloyDB over a pure single-purpose vector store. Imagine a marketplace agent.
A dual-purpose bot. A bot with two jobs.
Right. This agent needs to do two very different things. First, it needs to check the live status of my order, where is my package, and second, it needs to answer general questions about 50,000 different products. Does this toaster have a bagel setting?
This is the classic transactional versus analytical conflict.
Yeah.
And it trips up so many architects when they're first designing these systems.
Explain that conflict. Why are those two jobs in conflict with each other?
Checking an order status is a transactional query. It needs to be incredibly fast, precise, and absolutely consistent. If I paid for my order, the database must say I paid. It's high frequency, row-level access. You're looking up one specific order ID. It's like checking a specific locker in a train station.
And the product questions.
That's an analytical query. That's searching through a massive knowledge base, all those vectors we talked about. It's scanning through thousands, maybe millions of product descriptions to find the best conceptual match. It's a heavy, wide query that uses a lot of CPU.
So does the architect try to force one database to do both of these jobs?
You can try, and you will almost certainly fail. If your database is busy crunching vectors to find a toaster description, it might slow down the simple query to check an order status.
Mm.
And in banking or retail, slow order checks mean angry, lost customers. You cannot have your search bar crashing your checkout lane.
So the architectural lesson here is split the brain.
You have to split the brain, use a different database for each job, use something like Cloud SQL for the transactional stuff, the live order status. It's built for that kind of high consistency, row-level work. And use LODB with its vector support for the knowledge base.
So the application has two hands. One hand reaches into Cloud SQL to check did the user pay, and the other hand reaches into AlloDB to check is this toaster compatible with bagels?
Exactly. Don't compromise one critical workload to satisfy the other. Use the right tool for the right query. It adds a little bit of complexity to the application code, but it saves your performance and your sanity.
Now, there is another data problem that keeps architects awake at night. The source calls it training serving skew.
Ah, the silent killer of AI models. It's a really subtle but deadly problem.
It sounds like a horror movie title. What is it exactly?
Okay, imagine you're training a model to predict loan defaults. When you train it, you give it a massive amount of historical data. You tell it, this customer had an average daily balance of $5,000, and the model learns, okay, $5,000 is good.
Makes sense.
Now, you deploy that model into your live banking app. A new customer applies for a loan. The live app calculates their average daily balance, and here's the skew. Maybe the live app uses a slightly different formula. Maybe the training data excluded weekends from the average, but the live app includes them. So the live app calculates the balance as, say, $4,800.
And the model, which was trained on a different definition, says reject because the input definition changed without anyone realizing.
Exactly. The model isn't broken. The data definition is broken. The feature, in this case, average daily balance, was calculated differently during training versus during serving. That is skew.
And in a bank, that's not just a bug. That's a potential lawsuit if you're rejecting people for loans based on a subtle calculation error.
The regulators get very, very angry. It becomes a compliance nightmare. You can't explain why the model made the decision it made because the data inputs themselves were inconsistent.
So what's the architectural fix for this?
The solution is the Vertex AI Feature Store.
A store for features.
Think of it as a single source of truth for all your critical data attributes.
Yeah.
You define average daily balance once with one specific formula in the feature store. When the data scientists train the model, they pull the data from the feature store.
Okay.
And when the live application runs the model in production, it also pulls the real-time data from the very same feature store.
So it guarantees that the definition and the calculation are absolutely identical.
Identical. It ensures consistency from cradle to grave. It prevents the model from hallucinating or making bad decisions due to bad data inputs. It solves the skew problem by centralizing the feature generation logic.
It seems like so much of this, when you get down to it, is about consistency and auditability.
In banking and finance, it's 100% of the game. If you can't prove it and you can't repeat it, it didn't happen.
Which leads us perfectly to our final section, Section 4, operationalizing risk, or as I like to call it, how to update the software without getting fired.
Always a good goal to have.
We have a constraint here that's very simple. It cannot fail.
The classic, the highest bar.
The scenario is a retail startup or our bank that needs to test a new version of a model. Let's say it's credit approval model V2.0.
A very scary thing to update.
You cannot just flip a switch on a Friday night and have V2.0 deciding everyone's fate on Monday morning. What if it's broken? What if it denies every single loan application? Or worse, what if it approves every single one?
You'd be out of business by lunchtime on Monday.
So the requirement is we have to test it on only 10% of the live traffic first.
This is a classic pattern called a canary deployment, like the canary in the coal mine. If the canary stops singing, you get out of the mine immediately.
How do we architect this? Do we have to write a bunch of custom if-then statements in the app code to say if the user ID ends in a twen1, send them to the new model?
You could, but that's messy and brittle. You don't want deployment logic tangled up inside your core banking application code. The infrastructure should handle this. In Vertex AI, we use something called endpoints with a feature called traffic splitting.
How does that work under the hood?
You have one single endpoint, one URL that your application talks to. But behind that one URL, you have two models running simultaneously. You have model A, the old reliable one, and and model B the new hotness.
Okay.
You then go into the configuration for the endpoint, and you just say, send 90% of requests to model A and send 10% of requests to model B.
So the application has no idea. The app just sends the request to the same URL it always has.
The app is completely oblivious. The infrastructure handles the routing intelligently. Then you just sit back and you monitor. If model B starts throwing errors, or if the loan approval rate suddenly drops to 0 for that 10% slice,
You just turn it off.
you just update a config to send 0% to model B. It's an instant rollback with no code change.
And if it works, if the canary keeps singing,
You gradually ramp it up, 20%, 50%, and eventually 100%. Then you can safely decommission Model A. It is the only safe way to deploy critical models in a high-reliability system. It decouples the active deployment from the active release.
now let's talk about money, because even giant banks care about the budget.
Occasionally. Usually when the bill arrives at the end of the month.
The scenario in the notes mentions a scale to 0 budget requirement.
This is the no-ops startup dream, but it absolutely applies to big companies too, especially for internal tools or applications with spiky traffic.
Right. They need to deploy a model, but they don't want to pay for a massive, expensive virtual machine just sitting there idle at 3 a.m. when no one is using it.
A traditional VM is like leaving the lights on in your house 24/7. You pay whether you are in the room or not. If you have a massive GPU instance running for an internal HR bot that nobody uses on weekends, you are just burning cash for no reason.
So what's the architectural alternative?
Serverless. Specifically, using Vertex AI endpoints in a serverless mode.
How is that different from the VM approach?
It's completely on demand. When a request comes in, the system instantly spins up the compute needed, processes the request, sends the answer back, and then, if no more requests come in after a short period, it spins everything back down. It scales to 0.
So if nobody uses it for an hour, you pay nothing for that hour.
$0 for compute. It's perfect for irregular traffic patterns or for internal tools that aren't used 24/7. It perfectly aligns your cost with the actual value being delivered.
Okay, one last operational nightmare. The audit.
The clipboard brigade arrives.
The compliance team knocks on your door. They ask a very simple but terrifying question. That model running in production right now, model V2.0, exactly which dataset was it trained on, and which specific version of the training code was used?
If your answer is, let me go check Bob's laptop, or I think it was a data set from June, you are in very, very big trouble.
So how do we automate the answer to that question?
You use the Vertex AI Model Registry.
The registry.
It is the single source of truth for all your model artifacts. Every time you train a model that passes your tests, you register it. The registry automatically records all the critical metadata, the exact link to the dataset and storage, the version of the training code from your source control, all the hyperparameters you use, the final accuracy metrics. It creates an immutable lineage.
And immutable is the key word there. It means you can't go back and fake it later.
Correct. It's a digital chain of custody. This model came from this code and this data. In banking, if you cannot trace the lineage of a model, you cannot deploy the model, period. Because if that model later exhibits some kind of bias, you need to be able to go back and see why. Was it the data? Was it the code? You can't debug what you didn't track.
So the registry isn't just a fancy folder, it's a legal shield.
Ideally, yes. It helps turn the black box of AI into more of a glass box that you can peer into.
Finally, let's put it all together. We have all these discrete pieces: data extraction, model fine-tuning, evaluation, registering the model, deploying it. Stitching all that together with a bunch of manual scripts is just asking for trouble.
It's incredibly brittle. If the one person who wrote the script leaves the company, the whole process breaks. If the script fails halfway through, you don't even know where it stopped or how to recover.
We need an orchestrator to tie it all together.
You need Vertex AI pipelines.
What does that actually look like in practice?
It looks like a flow chart that you define in code. Step 1, extract data from the source. Step 2, train the model. Step 3, evaluate the model's performance. Step 4, a conditional step. If the accuracy is greater than 90%, then automatically deploy it to the model registry.
So it automates the entire workflow.
It automates the workflow and makes the whole process repeatable, reliable, and robust. It's what turns art into a factory.
And that really is the theme of this whole deep dive, isn't it? Moving from art to factory, from a one-off project to a repeatable architecture.
From can we do this to how do we do this reliably, securely, and legally 1,000 times in a row?
So let's synthesize the fortress we just built. Let's look at the final blueprint.
Let's review the plans.
We started with the compute. We chose TPU pods because we needed the ICI, that telepathic wiring, for massive training speed. We then mapped our different user groups to the right abstraction layer. IA for the innovators, PAYS for the builders, and SAS for the everyday user.
Check the foundation is solid.
Then we looked at the sovereignty constraint. For our German bank, we realized we couldn't use the public cloud API. We had to pivot to a hybrid or private model using open source weights running on our own hardware, potentially managed via the model garden.
The fortress walls are up.
We looked at the data layer, we split the brain, we used Cloud SQL for fast transactions and AlloyDB with vectors for the deep knowledge, and we used a feature store to make sure we weren't lying to ourselves or the model about the data.
The nervous system is connected and consistent.
And finally, operations. We used traffic splitting for safe canary deployments, serverless to save money on idle workloads, and the model registry to keep the auditors happy and prove our work.
The immune system is in place to protect the whole thing.
It's a beast of a system, but it's a system that's built to last.
It's built for the reality of high-stakes finance.
Now, before we go, I want to leave the listener with a final thought to chew on. We spent a lot of time talking about that no internet constraint, the idea that to be secure, you must be isolated.
The bunker mentality. It makes sense on the surface.
But here's the tension. The AI models of the future, the ones being built right now in research labs, are getting exponentially larger. They require a scale of compute power that is becoming harder and harder to fit into a single private data center.
That is absolutely true. We are approaching a point where the state-of-the-art model is physically too big and too power-hungry for typical on-premise infrastructure to handle.
Exactly. So how will banks reconcile this fundamental conflict? On one hand, the need for the smartest possible brain requires access to the massive hyperscale cloud. On the other hand, the need for the strongest possible fortress requires absolute data sovereignty and isolation.
It's a paradox, isn't it?
Yeah.
A real architectural dilemma.
The architecture of the future might not just be hybrid, it might have to be completely fragmented. Maybe you have a dumb but completely safe local model that handles most tasks, and a genius cloud model that you can only talk to in heavily anonymized riddles.
Or perhaps we see the rise of true sovereign clouds, all the power of hyperscale compute, but physically located and legally bound to a single jurisdiction. The cloud comes down to ground.
The cloud comes to ground. I like that. Something for you architects to mull over as you design your next unbreakable system.
Indeed. A lot to think about.
That's it for this deep dive. Go build your fortress. We'll see you in the next one.
Take care.